Thank you very much, and hello to everyone online. So, let's start off with what is predictive maintenance. And I always do like to start off at this point because whenever I engage with new people or a new audience, some of you would have heard about predictive maintenance, potentially even investigated predictive maintenance. But quite often, the understanding of what predictive maintenance is falls in line with machine magic rather than machine learning. So predictive maintenance is an evolution from traditional condition monitoring. But instead of having a specialist go around the facility, taking manual measurements, then uploading them to the computer, analyzing them, and reporting back on them, this function is now automated and online, so continuous. Also, with traditional condition monitoring, it was a snapshot in time. When I used to run condition monitoring programs, it would be once a month. You'd manage to get to that machine again on your route-based, time-based schedule, and you would take a snapshot to identify the condition of that asset at that time. However, with online continuous monitoring and an understanding of an operation, a machine's behavior, you can really start to get amazing insight into the condition of that asset, as well as highlighting signs of degradation. But like with any good condition monitoring engineer, a predictive maintenance solution should evolve and learn about failure modes, failure patterns, maintenance events, and give you recommended actions based off of that. It's also important to understand that predictive maintenance is not a technology, it's a maintenance strategy. Predictive maintenance cannot be installed in a site. Really, it's the usage of the information provided by a system that enables a predictive maintenance strategy in your environment. It's also not about predicting when a machine will fail. Quite often I get asked, as a requirement, we want to know a year in advance of exactly what the failure is and exactly the day it will fail. And the further out you're trying to predict a negative event like that, the less specific you can be. Really, what is of use to industries, maintenance teams, to project teams, is an understanding of the early signs of degradation with enough information that they can go and perform the corrective action when it best suits their teams, their production requirements, and their maintenance availability. It's also not a big data problem, especially when you're looking at cloud solutions and having to send large volumes of data to the cloud continuously. That can put a huge strain on your network requirements. So it's not about big data, really looking at the fine details inside of it and using machine learning to understand inherently noisy data. It's actually about providing the system with the good quality information, making it a solid baseline to learn from and highlight results. Predictive maintenance should also not be restricted to your high criticality assets or only your high criticality assets. The real value from a predictive maintenance program in your environment is to cover the entirety of its plant. And probably the most important factor, at least for myself, is that this isn't about replacing expert knowledge or skills you have. It's about making them more efficient. It's about scaling their efforts and availability in your environment. So to look at predictive maintenance, at the core of it is condition monitoring data. And this is data which can come from PLCs, drives, inverters. Even your process data is used for predictive maintenance. Things like flows, pressures, temperatures, understanding of batch requirements, and so on. Condition-based maintenance is then maintenance not done on a reactive or planned approach. However, it is done on condition when the machine or asset requires the maintenance to be done. Predictive maintenance sits around all of those and really enables a best practice approach to maintenance in an environment. And with technology being what it is these days, there is now the advent of conversational predictive maintenance. So this is now making the information accessible to everyone. And we will touch on that a bit more in a little while. But what does predictive maintenance give? What is the point? So I'm sure you would have all seen a PF curve within your time. So what predictive maintenance enables from the very early stages is when you start to see the signs of degradation, it will give multiple sets of early warning. So an indication that something is degrading with enough information that you can perform maintenance before your existing systems will set off an alarm before the process production machine has failed. But as I said, it continues to learn. So once it does learn and starts to understand what these signs of degradation mean, it can start to be more specific. So from the stage of early degradation, from those early signs, you may get some anomalies or trends detected. Then insight descriptions, letting the user know what is happening, interpreting the data. You may even get some prognostic forecasting and lead time to repair indications. Again, long before any conditions or thresholds have been violated on your environment, and your existing systems would have notified you that something's gone bang. Whoops, it's all gone wrong. So it's about giving insight early on that is actionable with enough time for users to make use of this and to plan in maintenance when it best suits the company and the environment they're working in. It's also important to note that predictive maintenance is not about thresholds. And this is something I personally have had to try and combat quite a lot in the eastern part of the world, is there are hundreds, if not thousands, of companies with hardware, sensors. They have potentially developed their own software solution, which is rule or threshold based, and they're selling that as predictive maintenance, and it just isn't. So if we look at the graph on the right-hand side, let's say that is the current profile being amps for an electric motor over a week period. So considering your production cycles, Monday morning, there's an idle period, and then you start producing production Y or X. Then you may go down for commissioning, pre-setup and an idle phase, and then you start in production for product Y. You may go down for a little bit of maintenance midweek, something which was planned in. You carry on with production of part Y or product Y, and then you tail off for the rest of the week. So that is an example of a typical production requirements and profile of an electric motor for a week's period. So with the system in question, these threshold-based, company will come in, install sensors, and possibly even set up some thresholds or limits for you. These could be based off of ISO standards, the size of the motor, the bearing type, the rigidity of the base and mounting. But there you have a simple threshold limit. Well, it is missing all of the important detail, especially around the operational complexity that you have. So maybe someone in your team needs to go and reset the threshold. Well, maybe the second time they have gotten it a little bit more right, a little bit more fit for purpose for an understanding of the production requirements for product X. However, it's missed the detail for product Y. So then the threshold needs to be reset again. And potentially this time they've captured or managed to get the right limit to capture the event that you're looking for. However, by this time, the teams on site that need to use this have lost trust in it. They've been over alerted. They've performed maintenance and essentially wasted money because there is limited understanding of the complexity of the asset and the production requirements. So really, it's not fit for purpose. What is needed, and especially within the pharmaceutical industries, is an understanding of normal production complexity, an understanding of your machine state. What is it trying to do? What speed is it running at? What product does it have or batch is it running through? What are the output capacity requirements? And with that understanding, a system which can highlight the specific signs of degradation with an understanding of machine state. And really, I think this is going to be a universal requirement, but also very specifically within the pharmaceutical industry, is a system which is applicable to every single type of machine that you have. You know, from your process environments, having your fermenters, chromatography columns, lyophilizers, all the way through to your warehousing and distribution. If you were to implement a solution or a system that is specialist in one of these areas, fantastic. I'm sure it will be very good at that one area. But when you look at the full range of production and environments that you have, you could now end up with 5, 10, even 20 individual solutions. Therefore, that is problematic. because you now have multiple logins, people that need multiple sets of training. It's really hard to truly understand the differences in capability, layouts, user interfaces between these different systems. What is needed in industry and in the pharmaceutical industry is one solution which is fit for purpose for everything. Predictive maintenance is evolving, and these requirements are very much in your grasp. So predictive maintenance, really, if we think about it as a online condition monitoring with automated knowledge and understanding, that could fall under diagnostics and statistical forecasting. Essentially, how is my machine, my process, my line behaving now? And how is it going to be behaving in the future, in a few days, in a few weeks, in a few months? The solutions that you are assessing should be able to prioritize maintenance. And again, this is not based off of machine or asset criticality. It shouldn't just be, oh, my very critical machine is degrading. I need to run off to that immediately at the first sign of an increase in current or vibration. No, it should be about understanding how concerned the user should be about an event, about an insight, and to be able to prioritize this so that your maintenance teams and project teams can decide which assets they want to work on, which is going to have the highest impact, or which is at risk of failing first. And we, with technology being where it is, and the huge boom in generative AI functionalities, generative AI and large language models have really revolutionized the predictive maintenance space, really making the information accessible to everyone, and also giving the ability to ask questions to the system which is doing the monitoring for you. So why would generative AI even be a thing? Why would it be used for predictive maintenance? Well, what we've found is that there is an inherent lack of data literacy. And this is at no fault for the maintenance teams. They are extremely experienced, extremely knowledgeable in maintenance, in engineering, in their field. However, expecting them to have any sort of data analytics skills is in many cases unreasonable. And what we found is they just don't. They also don't have time to interpret graphs. Most of the customers that we assist, their maintenance teams are stretched thin already. There have been a huge amount of budget constraints, limiting their team size, the team's availability, and really having to make do with what they have on site. So time is a huge thing. Also, whenever using a new system, who do you ask questions to? If it's just been installed and pre-configured, and then if you have to potentially pay the supplier for any bits of consultancy afterwards, you are very limited with the ability to ask questions and really get use from a system. Also, language barriers. For global organizations, you will have a wide range of languages spoken from your skilled expertise. So being able to speak to someone or experts in your native language so you get a true understanding is difficult. There's also the aspect of lost knowledge. I'm sure we are all facing and experiencing these challenges. In your environment, you'll have maintenance engineers who have been working with you or in your environment or in your field for decades. And now the up-and-comers, the apprentices coming through. So anything that your experienced engineers cannot impart onto the new up-and-comers, that knowledge is lost. And we all know of that person on site who can walk around and he knows when the homogenizer isn't sounding right. He knows that there may be something going wrong and can go and fix it just based off of that knowledge. That is experience which, yes, can be taught, but isn't always imparted on. So that type of knowledge and understanding of an environment, of a process, of a problem, more importantly, does get lost. It's also difficult to share knowledge and collaborate with global organizations. Quite often you'll find a company doing exactly the same thing. Maybe they have a facility in India and one in the UK, as an example. Their processes are pretty much the same. The products are identical. The machinery, maybe some variation on OEMs. However, they are like for like and extremely comparable. But how do they collaborate? How do they share knowledge between each other? Often we find these organizational silos in place. where there isn't collaboration, there isn't best practice sharing between them. And this is where generative AI comes in. First of all, it's about getting instant answers to your questions. So generative AI is able to interpret the data, the graphs, the data analytics for you and present it to the user in the natural language. It also provides the ability to ask questions to the system. The answers you'll get will be from an inherent knowledge, trained off of the knowledge on the internet. But for companies that are feeding their large language models with expert knowledge, it starts to become extremely powerful. So this expert knowledge could be in the form of condition monitoring techniques, maintenance and reliability practices, as well as user manuals, maintenance manuals, decision trees, and having instant answers to that expert knowledge and having instant reference to that knowledge is extremely powerful. Generative AI retains the knowledge forever. And I know forever is a definite term, but for the foreseeable future, we could say. Because it is going to continuously learn. It's going to have the store of failure patterns, of maintenance events. It has reference to the expert knowledge, your user manuals, maintenance manuals, and it can really start to build a deep, deep understanding of your environment and what is important to you, and make this knowledge accessible to all of you new up-and-comers, the apprentices, who don't necessarily know what this component's for or what the part numbers of that asset are. And it makes it extremely easy to share knowledge across all locations. Because as you would expect, large language models work in pretty much every language available. And because the users can interact with it in their native language and get results back in their native language, it means that your cross-country and cross-geography collaboration is heavily enhanced, really tying in all of this human knowledge into one space and making it accessible to every single one that uses the system. So really, predictive maintenance should be the convergence of the human-machine interface. It should be having a true understanding of your machines, of your processes, using your OT data, IT data, but also to learn from the human element, the expertise that you have on site. But predictive maintenance or any digitization program should be focused on business outcomes. And we'll discuss some of those in a while. An example of deployments within the pharma industry. This specific customer, they make insulin, and the machines that we're monitoring for them specifically is the vial filling line, so little vials. One of the key factors, though, is that we had to use existing data from their existing infrastructure. This wasn't a project to come in and install huge amounts of hardware, sensors, data collection devices. It was about, can we derive value from their existing infrastructure, their existing investment? And the answer is yes. Some of their success criteria and the pain points was on the silicone valves specifically, and the degradation that these caused. The fact that this company didn't have a centralized visibility, these were happening unexpectedly and halting production until they were able to inspect 20 or 30 silicone valves to find which one had actually failed. So we started working with this company in January 2023. Thankfully for us, and I would say for them as well, they actually had tried to develop their own system in-house. Unfortunately, that did fail. However, fortunately for us, it meant that they had done a huge amount of investigation. They weren't starting at a zero knowledge base. They knew what the complexity of predictive maintenance and had done a lot of the data work beforehand. So quite rapidly, a month and a half later, we had the system integration with data being pushed into the application. Their first success was roughly 6 months later from there. And this first success was just the first interesting event that was detected. And this also goes to show why going for your most high criticality assets isn't always the best approach, because high criticality assets are typically over-maintained. A huge amount of maintenance effort, time, and money is spent on them. So when you're looking at trying to achieve value and a return of investment, In a 12-month period, what is the likelihood that something interesting is going to happen, that something is actually going to degrade, that you can show results and show something working? So that is why we go for value. And again, I will discuss value a little bit later on in this presentation and how we target where the value is. But for this customer, even though the silicone valves were the main cause of frustration and loss in production, it still took over 6 months before anything happened for us to show results. However, with one notification, they were able to achieve a 3 times return of investment. By the end of that year, over 300,000 units or additional units were able to be produced because of reduction in breakdowns. So, early indication that something was degrading with enough time for the maintenance and project teams to assess when they wanted to do the production, to fit it in with their planned stops, and to still maintain production through all of those additional units. Huge amounts of value in a relatively short space of time. Let's talk about some of the challenges faced. Again, I would say these are quite universal. The maintenance of uptime. For maintenance teams, again, they are very good, very specialized, very experienced in performing maintenance. However, when do you perform maintenance? Well, when something fails. You know, the process is something fails, potentially an operator, pick up the phone, call the maintenance department and say, hey, my chromatography column has stopped, something's wrong. They would go out, then investigate, go back, plan in, make sure they have the spares, then go back through, perform the repair, make sure everything's tight and fitted, start it up, ooh, didn't quite get it right. And then they have to start the process of investigating, trying something new, and repairing it iteratively, let's say. That's potentially the worst case scenario, but still quite common. So without the visibility of the signs of degradation, the maintenance of uptime can be extremely difficult. Likewise, precise and correct maintenance, because in any environment, from my experience, about 5 to 6% of your assets or machines will have signs of degradation. But what about the other 95%? You know, precise and correct maintenance is about having an understanding that for the 95%, which are in perfectly good condition, that they're fine. Don't touch them. Don't induce maintenance, induced failure to them. They're in perfectly good condition. You can extend your planned maintenance intervals out a little bit until you have true trust and visibility of the signs of degradation, and you can fit that in with your production cycles and really benefit from precise and correct maintenance. In any environment, we all want to reduce the risk and operating costs. And a huge factor of risk is maintenance. The more someone has to touch a machine, the more risk and the more cost there is involved with that. I think what we're all finding is having separate systems which together make your entire production, but individually they are completely separate and really hard to talk to. So this is the OT-IT convergence. You know, your OT environment, PLCs, drives, inverters, automating a lot of your process, along with IT systems such as your maintenance management system, or even your EAM, ERP systems, which together give you a nice big picture, but they are still separated systems. They don't talk to each other, and they make a true understanding and true value extremely hard. And sustainability. You know, this day and age, we do all need to have an eye on our sustainability and carbon footprint, let's say. This is also compounded by scalability. Again, I spoke about a single solution to monitor everything, and also not being specialist in any one area. In an environment, we need to have the effects of scale. It needs to be scalable. And not scalable in the sense of throwing more humans at it, more resource at it, more money at it, but truly scalable. Something which can target your data silos. You know, I spoke about the difference between IT and OT, but what about within those systems? You know, the individual OT layers of infrastructure talking to each other, being able to be interoperable and really get the value together. There is a skill shortage going on. skills in the sense of new maintenance engineers, new production teams, people not wanting to be influencers or social media personalities, but going into the STEM world, really. Adoption is always going to be a massive thing in any digitization project, any kind of predictive maintenance uh, project that you would run. Getting the human element to start using a new technology, a new system, and being happy with it, as well as collaboration and engagements between your global teams. And then if we look at something more pharmaceutical specific, regulatory compliance is massive. Your GXP processes are insane. I'm sure a lot of you will know the trouble you have to go through, even just to drill a single hole within your process environment. The amount of paperwork required to drill a hole is huge. Within pharmaceuticals, however, my lights have gone down. Give me 1 second. There we go. Apologies for that. Within the pharmaceutical environments, the processes are complex. The machinery is quite complex. A lot can happen with your loss in production based off of very small things happening inside of the internal workings. So a true understanding of the complexity of the machines and production is a problem or a challenge. The high cost and loss production for pharmaceuticals, as you all know, is huge, especially when you start looking at, in a sense, batch production. So if we look at fermentation, starting off at 2 liters, then going to 20, then 200, 2,000, 20,000. If any one of those fermentation processes were to fail, you are losing that 20,000 liter capability, even if it starts off at the 2 liter point. So it has a huge cost implications, along with product quality. If contamination gets in at any one of those points, you've also lost the 20,000 liter capability in your production. And of course, cybersecurity. I don't think any one of you would want your IP getting leaked or even being held under a cyber attack and being held for ransom. These are extremely, extremely costly events that could cripple or have huge, huge dire impact in your environment. Now, predictive maintenance often gets confused with predictive analytics, or at least there are approaches which rely on pre-built machine learning models or customized model creation. And essentially, I'm not going to go through all of these in great detail, but you can see there are multiple steps which take a huge amount of time. So your problem definition, roughly 3 weeks, data collection, another 3 months, getting data at a huge high frequency rate. There's a exploratory data analysis, which takes a team of data scientists weeks to perform. Then algorithm selection and model development, making it fit for purpose to take into account all of this complexity and huge volumes of data. There's the evaluation in a real world environment, making sure that these are fit for purpose. The rollout, again, could take a number of months, and along with post-deployment monitoring, which is ongoing. Time to value for these approaches is 14 to 24 months. It's a huge amount of time, and this process that I've just described has to be iterated for every single machine type you have. So that really means to get value out of these takes a huge amount of time, a huge amount of resource, and a lot of your efforts on site will need to be put into helping create these fit for purpose models. Really, what the industry needs is something that can be deployed once and scale. You're not looking for something which is specialized and runs through this iterative process and takes huge amounts of time, as I've said. You need something which is fit for purpose and can be deployed rapidly and scale from your site in the Northern Hemisphere, Southern Hemisphere, and all over the world. So how does Siemens do this? For us, it's important really to identify and define condition indicators. So condition indicators are derived from time series data. They come from condition monitoring data in the pharmaceutical industry, as specifically also process data. But it's derived from your process and condition monitoring data to expose signs of degradation, and it is to give you leading indicators of failure. It also helps to reduce the amount of noise within the data, because a current profile for an electric motor, again, can have a huge variation in normal operating condition. So when we start to expose condition indicators, you provide a more stable baseline understanding. And condition indicators can be created in a range of places within your infrastructure, derived in or on the edge, within factory historians, SQL databases, or even cloud-based systems. And I'll give you some examples of these condition indicators. So we've got three assets as the examples. There's a robot, a pump, and a conveyor, quite universal. So if we will look at the robot, we may be looking, or the condition monitoring data is potentially torque per axis. However, we want to capture this data or process data to be consistent, because if this is a palletizing robot, well, it could be picking up different weights and configuring them, or it could be running at different configurations of product placements on your pallets. Therefore, a huge variability in the data, the torque requirements in any given period of time. So a condition indicator for that, or an example of a condition indicator, could be the max torque per axis after the last movement and its return to home. This is an unloaded movement, and it brings consistency to the monitoring of these axes. For a pump, the data could be input and output pressure, but we may look at min, max, and average differential pressure across the pump. Again, by looking at your min, max, and average, you're still understanding the profile of those measures while heavily reducing the amount of data you send to the cloud and bringing stability to those. Also highlighting when one of them changes, because your minimum and average could be relatively stable, but if your max differential pressure is increasing, that could give you an indication for individual events happening which are affecting the pressure. Motor currents, we could look motor current for the drive of the conveyor. We could look to extract statistical characteristics like your peak start current, your mean running current, and your peak running current. Again, still giving profiles of the behavior while bringing stability into the monitoring. How do you deploy scalable predictive maintenance in your environment? At Siemens, we have come up with what we believe is a best practice approach to investigating, implementing, and scaling predictive maintenance, and it's designed to be customized to your environment. So this methodology comes in 5 phases, and we'll go into the detail of these, but this is scope, design, deploy, operate, and refine. And it is the best practice approach that we have created fit for purpose for us. If we look at these a bit further, scope, this is typically pre-contract investigation, getting a true understanding of your environment, the complexities that you have, what is specific to you that we need to take into account before we can say, yes, we will have a successful project. So understanding the value and benefits. For predictive maintenance, how do you define what is valuable and where the benefits lie? Starts off with maintenance time. So for your global operations, let's say you have 4 or 5 factories around the world, which one of them, if we were to list the reactive and planned maintenance for each of them, we would then get a total time. The factory that has the highest total maintenance time, that's where we now bring into focus. Perfect. So we then split that up into the various areas, your upstream, downstream, and services. So again, which one of those have got the highest maintenance time? Perfect. Well, it's actually your utilities and services. And then we can start to focus on machine types and so on. We also then look at the specifics of your environments, the infrastructure, the data availability, the people involved, and their time. We try and develop a project team with the right characters involved, and then create a project plan and a proposal with all of these factors considered. Design is when the project starts, and it goes even deeper into the investigation. So there's a look at the assets, the assets that have been identified and selected, but you look at the operational complexity and operational interdependency of these. We look at how these machines and assets are failing and what data is available to cover those. We can also do a gap analysis to see, is there need for additional sensing or additional data? We make sure that we define the goals and success criteria with the project team, and we look at the data architecture and data transformation capabilities. From there, we get into the deploy phase, which is about making the data move. So if there is need for additional hardware installations, sensor, data collection, and so on, that gets done, that the data is then processed and streaming through to the cloud. We make sure that the assets are onboarded, the users are onboarded and trained, and any contextual data is also fed in to the application. We then go to operate, which runs through a best practice approach on using the application. So how to monitor notifications, how best to add in maintenance events, how to do daily, weekly, or monthly case reviews, as well as periodic reviews of the system. And then in refine, it's about making it as good as it can possibly be. So we look at the need for additional data or additional processing of the data. We look at who is using the application. Is the technology being adopted on site? Because without people using it, it is useless. So our customers have got many different approaches on the adoption factor. Some of them will define a single or a small group of PDM champions. People whose responsibility it is to log in daily and make sure that the information is then distributed to the wider maintenance teams. For other customers, they make sure the entire maintenance team has a responsibility to log in and incorporate the knowledge into their day-to-day. So for your area that you are responsible for, you need to make sure you log in, looking at the new notifications, and bring that to the morning stand-up so that you are on top of what has happened overnight and what your plan is for the day. Also look at what value has been achieved and how do you scale that outwards. And value for predictive maintenance can come in many forms. Downtime avoidance, spares reductions. You can have planned maintenance efficiencies and even pushing those planned maintenance events out. Less consumables and even less of a carbon impact because environmental assets have not gone down. You had less spills of chemicals or even oils, let's say. And then finally, we look to integrate into daily workflows. So this could be an integration with your maintenance management system, or even providing the information into whatever systems best suit your day-to-day. And if we look at how this project plan can roll out, it can follow something similar to this. So for the asset selection process, this could take about 2 weeks. Also, starting in week 2, we would look at the data architecture and the data transformation. At week 5, we could be looking at the pre-processing and data streaming through to the application. And in week 6, the start of the onboarding and configuration, which also means at the start of week 6, there is now data and valuable insights within the application. So users can really start to rapidly gain value from a solution if implemented in the right way with the right project plan behind it. But for the human element, the people on site, you must be thinking, wow, this is going to take a full team of us, a huge amount of time and effort, and really we are already stretched thin. And the fact is, yes, it does require time. If you're going to undertake this process, be prepared to invest in time. However, we have found that the initial stages are resource intensive to a certain extent, but however, scaled or steady state usage is quite easy and doesn't require a huge amount of time. And if we were to look at the person or the character within the project from your teams, who would be the most prominent, it could be the maintenance engineer at roughly 2 hours per day in the initial stages. That is during your commissioning and asset configuration. But once the onboarding has taken place, once the training and the adoption and confidence in the system is there, that then goes down to half an hour a day. It's not about giving your teams an additional thing to use, an additional responsibility. It's about giving them information which is easy to access, easy to understand, and is going to make their efforts in any day more efficient. So we can run through a bit of a process together. Let's assess your data and cultural readiness, because these are two aspects which are extremely important in any project. So we start off with the data evaluation. We've got 5 categories here, 1 to 5. 1 being no sensors installed, poor access to control systems, and no maintenance records or no maintenance recorded. Your ranking of 3 would be an online, raw, or simple data captured, potentially from systems, or you have some access. Ooh. Sorry, fire alarm. There we go. So 3 is online or raw, simple data captured, potentially from sensors, or you have access to some of your control systems, potentially even a historian, and you will have access to some maintenance data recorded electronically. And then 5 being online condition monitoring data and advanced condition indicators coming from sensors and control systems with the ability to stream this already through to the cloud. And your maintenance data is available via integration or export through a CMMS. Then there's the cultural evaluation. So again, 1 to 5, 1 being the maintenance strategy is mainly reactive. You'll have some planned work done. There's no PDM in place, or not even traditional condition monitoring in place, and no real KPIs or targets to increase capacity. And this is more in line with a mom and pop operation, let's say. Your ranking of 3 is your maintenance strategy will be extensively preventative with the use of condition monitoring and potentially even a PDM team being established. And you will have, as a company, targets to drive up efficiency and productivity. And then 5 being an extensive preventative maintenance project or plan strategy underway, with PDM being investigated, or maybe you've even done predictive maintenance in the past, and your company has clear and ambitious KPIs and targets. So from there, we can then give a functional maturity, which is essentially an aggregation of these 2 elements. Basic group-based condition monitoring through to automated condition monitoring, which is where we would really start at. And then full prognostic capabilities being a 5. But using this ranking, we can give a project, or we can predict a project success using these elements. So how likely are you to succeed based off of a very high level understanding of your data availability and your cultural availability? But if you find yourself on the lower end of the scale, don't worry. There are definitely ways to develop both data and cultural maturity. So from a data perspective, this could be starting off with additional hardware and sensors. Let's get some vibration, current, temperature sensors in place so that you can start monitoring. Then you can start looking at your OT environments and your existing data availability, and how would you make that data accessible, all the way through to having specialists configure the algorithms and machine learnings to be very specific in understanding your assets and machines and their requirements. The cultural maturity, for companies that don't have the people or culture in place, we can increase all of this by awareness, market studies, educations, workshops, full in-depth training, and looking at specifics within your environment. And even for those who are already starting at a mature state, you could look at getting people within the project team involved in wider communities and start to become real champions of predictive maintenance in your environment. And then calculating a return of investment, because essentially every project needs to be of value. It's important to understand, though, when you start a project, there is a difference between a proof of concept and a proof of value. A proof of concept is about testing the technology. Is this going to work in my environment? Is the technology going to give results based off of the complexity of my machines and areas? This is really about small number of assets, probably for a short amount of time, less than 6 months, to see, is this going to work with my infrastructure, my data, my machines? That's a proof of concept. But at this point, you cannot expect realistically to get an ROI. Maybe you get lucky, probably not. It's about testing the technology. A proof of value, which is where we drive our projects, is about getting an ROI. It's about really testing the methodology. So still seeing, do I have the right data, infrastructure, machines, and is this system suitable for my data, infrastructure, machines? But also, am I going to get the adoption by the users? Is it easy to interpret and get value from? And am I going to essentially save money by implementing this solution? But there's a full range of aspects for success, and it really does depend on your project size. So if we look at the table on the top left-hand side, there's a proof of value. This is typically a single area for less than 12 months, or maybe even up to 12 months, but still on a limited number of machines or assets, between 50 to 100, let's say. And what can be achieved with that is avoiding potential failure on those machines. There is capturing the maintenance activity, and then knowledge capture with the generative AI. When you start to move to a larger phase 1 project, being a single area for 12 months, maybe potentially more, that's when companies can benefit from uptime improvements. However, when you go to a phase 2, which is looking at hundreds of assets in an environment for at least 12 months, that's when you would benefit from efficient maintenance, better maintenance planning, asset lifetime extensions, impact on your safety KPIs, planned maintenance reductions, and avoided overtime. When you're looking at multiple sites, that is when you can benefit from all of those good things, along with energy efficiency, reduced labor, and OEE improvements on a large scale. And when you go for a global expansion, that is when a predictive maintenance program can really, really impact your sustainability goals. So I would like to thank you all very much for your time.